Thanks everyone for having me. So Ricard already introduced me. I'm Théo Fidry. I actually live here in Barcelona now, although I don't speak Spanish yet. You can easily find me on Twitter or GitHub with those handles. So before getting started with mutation testing itself, I would like to talk a bit about the problem it solves, because I think it gives you a better understanding of how to use the tool, when to use it, and if you need to convince people about how to use it, well, it's going to be easier for you to explain it if you know what it is for. And for that, we're going to talk about software quality. So Marcelo Duarte, if you're not familiar with him, he's the creator of PHP Spec specification framework, and also a very nice person. So according to him, software quality is to what extent the software takes into account what matters for customers and the maintainability of the source code. And the interesting thing here is there's actually two kinds of qualities. The first one is the external quality, what matters most for customer, and second one, the internal quality. So to illustrate it, because it's obviously easier to show what's not good than what it is good, so for those who don't recognize, it's Internet Explorer and the Windows XP with all the installers, all the tools that each installer program wanted you to install if you didn't tick them off. So external quality could be defined as the conformity to user expectations, the reliability, the accuracy, ergonomics, design, and you can probably fit a lot more things, but to sum it up, it's the quality perceived by the user. And the internal quality, so here it's a report of Central Lab Insights, quality analysis tool. And so on that report, you have about 20 critical issues, 700 major ones. So even though if you can question the tool and there's some false positives, it looks pretty bad. And so internal quality, please, right, could be defined as by its maintainability, the cohesion, simplicity, clarity of the code, and obviously can fit many more criteria. But in essence, it's the quality perceived by the developer. And we're going to focus on that one for now, because the other one is like a pretty big topic as well, and could use more than one talk. And so the first question is, should we care? The answer looks obvious, but it's interesting to know to what extent at the very least. So the first thing you can look at is the stamina of a project, which could be defined by the number of cumulative functionalities over time. So I'm sure you may have seen this graph a couple of times already. So in red is if you don't care about it at all, you can see that it's pretty easy at the start, but the number of functionalities you can add steadily goes down over time. So it's harder and harder to add some. Whereas if you do care, it's harder at first, but then you pick up a pace and it's pretty much constant. And while you have the sources if you're interested, but it does kind of make sense because as you get more code, more functionalities, when you're going to add a new piece, there's more things to account for. And the more you care about the quality, the easier it's going to be to add that piece and make sure that you didn't break anything. The time at which that happens depends at the point where you care brings benefits. Kind of depends, depending on the team, the kind of project you're working on, the kind of complexity you're dealing with. It depends on multiple factors, but it's usually a matter of weeks. So the less you care, the harder it will be to add new features over time. A second thing we can look at is the cost of a bug, the same bug, depending on the phase at which it has been discovered at. So according to this graph, one bug could cost about $100 at the development phase, if it has been discovered there, and could cost you 10,000 if you discover it at production. Again, you can question those numbers, how it's been calculated and blah, blah. You have the sources, but it intuitively makes sense as well. If you take, say, a payment system, and suddenly some customers cannot pay anything, or some other customers needs to pay, get charged twice instead of just once, well, it's going to cost you the time of detecting that bug, fixing it, testing that you fixed that properly and you didn't break anything else, deploying that fix on production. You're going to need to refund some customers, maybe give a coupon or discount. It's going to affect your image. All those things are hard to calculate. I mean, it's hard to calculate the cost of all of that, but it does make sense that it's much, much more than if you just discovered it way early on while you were developing, where it only affects you and your time as developer. So the origin of the cost, if we break it down, usually it involves the building cost, the cost of debug and repair, assuming this is no longer happening at development time, and the technical debt, which is a way to say that the more complex your system is, the harder it's going to be to add a new piece. And if you care more about the quality, so the building cost is going to take a bit longer because you're spending more time on it to get it right. You hopefully don't have any bug with it, or at least much less. The technical debt is going to be likely going to be smaller because you will have had the time to make sure that the debt introduced is lowered, that it's going to be easier to add a new piece later on. And so there is going to be a difference of cost overall, and that's the cost of delay. That's the cost of that neglect that you had because you didn't care about internal quality. So the more you delay that, the more expensive it's going to get over time. This is why for prototyping you can get away with it because it's probably just going to be for a very short time, very small scope. But for a product or something that's going to live longer, it's going to cost you more. So yes, you should care, obviously. Now the question is, how do you improve it? And one answer, because there's other things you could do, is by adding tests. But at least for automated tests are also code. And that matters because like the rest of your code, you need to write them. You need to make sure that they work. You need to refactor them. You need to maintain them. So the tests, I don't like the word expensive because it's a bit prohibitive, but they have a price. They don't come for free. You can't afford to have like a feature that takes 1 day to implement and spend 10 days just writing tests. That's too expensive. So you have a kind of balance to find, and they introduce their own set of problems. How do you safely refactor your tests? How can you make sure that given test suite, you have an idea who wrote it? How do you know that you can trust this test suite, that it's retesting anything, or if it's just bullshit? How do you make sure that the rest of your team is writing effective tests, and so the tests that are needed, not writing tons of tests just for the sake of it and saying that you wrote tests. Or when you have a feature that was not tested, for example, legacy code or something, you're writing tests for it. At what point, how do you know that you added enough tests to capture all the existing behavior? So in short, how do you assess the quality of your tests? And so a way to represent it is if that red dot on the cursor is level of quality, on the left-hand side you have no tests, On right-hand side, max test, which is, in theory, a point you should never be able to reach. The more you tend towards a no test, the more velocity you will have on the short term at least. Because, say, if you add a new feature, you just have this new source code to add. You're cutting down the test, so there's less things to add. You're more likely to break something. It's more likely to cost you, but it's faster. I mean, at least the perceived speed is going to be higher. And the more, on the contrary, the more tests you have, well, you have more code to write, or you have more code to refactor. So obviously, it's going to take longer, but again, probably going to be cheaper in the end. And the thing is, I'm not saying you should be on the right-hand side or left-hand side. It depends on you. What's important is we should have kind of a way to measure where we are at, and then it's you, depending on the context, that needs to decide if you're in good position or if you need to move faster or not. If you're a startup, you probably want to keep a high velocity because if in 6 months you don't secure fundings because you couldn't deliver a feature, then your startup is just going to die. It's going to be work for nothing. On the other hand, if you're an established product, you want to cut down on the cost of the bugs and you want to improve your quality, so it's more important to be more on the right-hand side. So we get to a point where we need to assess the quality of our test suite. And the common answers to how we can do that are, don't worry, be fine. If that's more the careless approach. I'm a ninja rockstar. I know my tests are good. So it's like this guy that thinks he's genius, and often he's not. And I mean, even if you're a genius, you won't test, at least for other people and yourself. I do TAD. I know my tests are good. It's not necessarily a bad answer, but then again, when you look at tests, there's nothing that tells this has been done TAD way. You also don't write all the tests in your code base unless you're alone. And when you need to refactor your test, how you test drivers changes. And then you got code review. Code review is actually a pretty good answer, but it's inconsistent in the sense that depending on who does a code review, how much knowledge that person has, how focused that person is, how much time that person can spare, you're gonna get very different results, and it's quite labor intensive. And the last one is code coverage. Now, that last one is interesting, but completely wrong, because line code coverage does not tell you what has been tested. To illustrate that, we can have take this simple class. So this class is called counter. It has a public count property starting at 0, and a count function to which if you pass a number and the number is superior or equal to 10, it's going to increment the counter. Like, super simple. And so for this class, we have 2 tests. Now, I'm not too interested in the actual implementation of this test, so hopefully the name of this test method is self-explanatory. So one of the tests counts that if you pass it a number above 10, it's going to increment the counter, good. And that if that number is below 10, the counter is not going to get incremented. So we have those 2 tests. We run PHP units with code coverage, and we have 100% code coverage. And the question is that good enough? To know if it's good enough, a simple way to do it is by introducing a bug. So here we change superior equal into superior. And we run the test again, and they pass. Which is not good, because you introduce a bug. Your test should be able to pick the bugs you're introducing, either because, be it a change you wanted, or be it a bug introduced involuntarily. So your test still pass, and your test suite is deficient. And if you look at the code coverage HTML report, rather, that comes with PHP units, you can see that, yeah, this code is covered, but legend tells you it's not like tested, it's executed. And if your code is tested, it is necessarily executed, but the reverse is not true. So actually, the only thing, if there's one thing that line code coverage can tell you, it's what has not been tested. Because if your code has not been executed at all, it cannot be tested. So in our previous example, we were missing the case of when we're passing 10, that it decrements it. As soon as we add that test, we run our test again, then our test suite picks up the bug. So how do we detect that a test suite is deficient? Well, like we just did, by introducing a bug. And this is what mutation testing is about, automating that process. So to present it another way, you take your source code, you take a mutator, and there is a mutation process going on, and you get a mutant. Well, I love those pictures, but unfortunately they don't quite explain really what's going on. So if we take our source code, yeah, it's a bit more boring. One mutant is the change we introduce, changing the compilation we're doing. That could be a mutant. So most of mutation testing tools work pretty much the same. There is differences between each languages, but they're quite subtle. The overall mechanisms are identical. So here's an example of a couple of mutators you could find, transforming the plus into minus, superior equal into superior, swapping the operands of the spaceship operator, returning false instead of true, and you can guess there's tons of it. So the way mutation testing tool is going to work is it has a file collector that's going to try to find the source codes, the source files in your project. So here it's going to be the file counter and foo. And so once we have those files, each mutation testing tool comes up with a list of mutators, and for each source file, it's going to run through each of those mutators to generate a list of mutants. Those mutants at that point are just a change to be made, but the source code has not been changed at all yet. And then, so here's an example of a couple of mutators for the source code earlier. We can change the symbol, we can change the magic number 10, we can change the incrementation into decrement, and there is more of them, but that gives a good idea of what can generate. And then for each mutant, we have a process builder that's going to create a process in which it's going to apply the mutant, i.e. in which it's going to mutate, change the source code. And a test runner that is going to run the test in that process, and so we're going to get the result. Did the test pass or not? If the mutant did not cause the test to fail, we say that it survived. So it means that the bug that was introduced was not detected by the test, which is not good. If, on the other hand, the test failed, the bug was picking up, we say that the mutant was killed. So from that, we can get the mutation score, which is number of mutants we killed over the number of mutants we generated. And ideally, we want all the generated mutants to be killed, so the score should be 1 or 100% if you multiply it for getting percentage. So how to detect that if test is deficient? Well, in the end, you don't have one, but two metrics. The first one is a line code coverage that can tell you what is not tested. And then among the executed code, the mutation score can give you what is definitely tested. Now, you might have noticed with the previous mutants that the changes were really quite simple. And that begs the question of if it's really going to work out for a real application, if those small changes are really going to help you out to detect any bug. And actually someone demonstrated that if for a given complex application, if you detect all the small faults, you're going to pick up most of the complex ones. So it's actually not just test, I mean, it has been demonstrated, so it really works. Now, because we're interested in PHP, how we do mutation testing in PHP. So you actually have two libraries, Humbug and Infection. Humbug was the first one, but over time it got unmaintained, and Infection came up with new innovative ideas, and over time, because it just doesn't make sense to have competition at that level, Humbug has been deprecated for Infection. So to start a demo, to show how that works in PHP, I picked Infection because we don't have a choice, and Symfony dependency injection. Why that package and not another? Well, I'm biased since I mostly work with Symfony, and more importantly, it's quite a popular package. It has non-trivial code, so if it works there, it should work in most places. So for the demo, we cloned the package repository, installed dependencies, we installed Infection, and then PHP unit. Nothing fancy so far. The repo already has a PHP unit configuration, so again, nothing special there. We just tell where the source files are. And we try to run PHP unit, just to make sure that we didn't miss anything. And all the tests are passing. And it takes almost 2 seconds. And then we initialize Infection. So Infection helps you prompt your helper to get to create the configuration file, and that's one possible result. So it's not very complicated in the end. Source, where you tell where the source files are. PHP unit, because PHP unit here has been installed as a file, not as a dev dependency. So we need to help out Infection a bit, tell it where PHP unit is. And logs, well, to get more information later on. So then we run Infection. It's quite big. And it took 50 minutes. So to break it down a bit further, so first, Infection is running with Xdebug enabled. The reason for that is that Infection needs code coverage tool. So here we pick Xdebug. You could use PHP DBG or pcov, which both are much faster. And then Infection runs the test suite again with that coverage tool to generate the code coverage of your test suite. And you can see that it actually takes 20 seconds instead of 2 seconds earlier without Xdebug. And then Infection generates mutants, and for each mutant, it runs a test, and the mutant is going to be killed or escaped. And after that, you get a nice summary. So here you can see that Infection generated almost about 3,500 mutants. And you get the code coverage of that, which is 82%, which is pretty good score, really. Keep in mind that this library has been developed without infection whatsoever, so it's like a pretty good result to get when it's not a metric you monitor. And then the log file tells you a bit more about what's going on for the escaped mutants, because that's what you want to look at, see what you missed exactly. So here you can see it's the path of the file that was changed, the name of the mutant, the command infection used to run the test for it. You get an actual diff of the mutant applied, and the PHP unit output for this test. So hopefully this should be enough when you want to look at what you missed. This should give you enough information to know what to look at and give you an idea about what test to add. Now, that's a simple way to run infection, but there's like a couple of tips you can apply. The first one is, well, you don't necessarily need to run infection of your whole code base all the time, especially if you're interested in testing just like one or two files because you're debugging it or you're just testing a specific feature. So you can pass a filter option where you can tell which source files to just keep and mutate instead of the whole code base. And this ugly line there is, well, documented, and you can copy, paste it from documentation. It's really useful for, say, your CI to run infection only the files changed for your pull request instead of the whole code base. It's also, if I remember correctly, it's a similar command for PHP CS Fixer and other tools. So it's pretty standard command, although it's quite ugly. And a nice option as well is the min covered MSI. MSI stands for the mutation score. So since you get mutation score from it after running it, you can also enforce a minimum score you need to reach to prevent any regression. You can also run infections on multiple threads. We don't do it by default because, well, most PHP testing tools don't run things with threads by default. So actually it turns out that for most applications, most tests, you might need to adapt one or two things to be able to run them into threads, or simply if you have, say, integration tests that depends on the database, you will need to do some adjustments if you want to run them in parallel, otherwise you will need to exclude them from infection, for infection to not attempt that. The command is slightly different in OS X, but otherwise you can just pick an arbitrary number. It doesn't really matter. And another option is only covered. So for historical reason, infection picks try to mutate all the source files you give to it, including the ones for which there is no test. And so this option will make sure that if it's going to look at the test first, and if there is no test that has been found for this given file, it's not going to attempt to mutate it. So it's going to reduce the number of mutants generated. I actually personally believe this should be default, so if you believe so as well, you can check on the repository, open an issue about it. You can change things. And then one last useful thing is, if you look at the configuration file, there's tons more options that are documented on the infection website. So here you can see the thing at default, at function signature, are referring to profiles, which are sets of mutators. So you could set, yeah, here we run the default mutators. The profile function signature contains several mutators. If you can turn it off. You can also, for a given mutator, you can in your specific file or specific method. So that helps you out with the false positives. Say, like, yeah, this mutant, well, actually it's legit, or I actually don't want to care about this case. So this allows you to configure it. Now, with just those small changes, so just running on only covered and with threads, the previous command that took 50 minutes is now taking 6 minutes. And the main reason is the difference of mutants generated. Sorry. So when I discovered mutation testing, I found it really interesting, and it looked to be working, although a bit young. And as I dig further into it, I found out that it was actually quite old. Like, we were already talking about it in the 70s. So that begs the question why is it not widely spread 50 years later? And turns out there is indeed a couple of problems. The first one is a maturity problem, because although we started to talk about mutation testing as a tool in the 70s, it was still more as an academic tool with not really any practical usage, or at least any usage in the industry. And I think the oldest mutation testing library still being used today is 7, 8 years old, not more than that. So it's actually not that widely used yet, mostly because the tooling is still actually quite young, although the technique was known for quite a bit already. You also have an integration problem. Basically, all the tools are not, because they're all not super mature, some of them only require you to run on the whole code base all the time, which is super slow, and obviously we don't want to wait 50 minutes for your test to complete. And there was no easy way to integrate it in the CIs before, or even like 20 years ago, was there even any CI yet? So this is hopefully a problem that's getting, solved at that point, but it's still quite recent. And the last but not least is it's a brute force technique. What that means is if you have n number of tests and you have m generated mutants, the mutation testing tool is going to run n by m tests. So to give an idea with the previous library, Symfony dependency injection, there was about almost 700 tests. That took about 30 seconds, and we generated 3,500 mutants, which makes about 2 million tests, which, if they're as slow as they were, would take you over 50 hours. I don't think anyone wants to transform a 30 seconds test suite into 50 hours. That's not very reasonable. So luckily, there is ways to optimize this. The first one is to mutate only the covered code, so we reduce the number of generated mutants, and if there is less mutants, there is less tests to run. Incremental analysis, i.e., again, on a pull request, you're changing only some files. You don't want to run the mutation testing tool on all the files. It doesn't make any sense. You just want on the change ones. That's the only thing you're interested in. So the scope is going to be much smaller, hence the time it's going to take much more reasonable. Parallelism with the threads. Equivalent mutant, this one is more about internal optimization. i.e., some research papers suggest that there is multiple mutants that are actually redundant. So if the tool can detect that those mutants are redundant and just picks the necessary ones, we reduce the number of mutants again, so faster. Different level of requirements. Basically, the idea is that in any real-world application, There is some stuff that you don't care about nearly as much, like some commands that are meant to be run one time or for which it has some infrastructural concerns that are easier to test manually than to try to write tests for it. Whereas some parts, like more your core domain, you want to make sure that this really works. So you could, ideally, it would be nice to have be able to configure the tool so that we are really exhaustive about the mutants generated for the core domain, but for less interesting ones, well, to be more flexible about it. So already with some of those optimization strategies, infection doesn't do all of them yet. We went from the theoretical 53 hours to 6 minutes, which is much more reasonable. Still a big difference between 30 seconds and 6 minutes, but at least we can run it. Now, I mean, infection is still quite young. Like the project is 2 years now, which in open source is like super, super young. There's still quite a lot of things that could be added, more optimizations that could be done, or to make it easier to use. So some of those works that could be done is, for example, the support of different testing frameworks. Right now, it only supports PHP unit and PHP spec. And still, I mean, it would be nice to have at least for Behat, Atom, and Conception, like at least the most popular ones. The equivalent mutant problem, infection doesn't tackle it at all. So for example, the mutant above it's really equivalent. It doesn't do anything. And this, if there's some of those mutants that are generated, it would be interesting to know what kind of percentage are they, and if it's interesting to implement strategy to try to mitigate that. Another example is you have 2 mutants, like applying only one of them is enough. So again, same problem. The research papers mention about 30 mutants, but again, those papers don't really have any code to show what they used for their measurements. So it's a bit hard to tell if it's really a realistic number or not. Granular configuration. So right now, the only thing you could do is have multiple configuration files, say a configuration file for your core domain and one for like a more peripheral part of your application, and specify which configured file to use for infection. It would be nicer, I think, to be able to find a way to have only one configuration file for that, but it's still up to discussion. False positives tracking. So the idea is that some mutants, I mean, there's going to be false positives, i.e. mutants that you cannot kill either because it's not worth your time or because it's a case that cannot happen in your context and that is not worth, I mean, you don't have an easy way to tell this cannot happen. And for that, infection will just log everything in the log file, and you have no way to say, oh, this one, I checked it, it's a false positive. So when you run infection again, it's going to appear again. It might or not be a real problem. We don't have a lot of feedback on that. So if you're trying infection and you find that you have a lot of false positives and it's hard to track them, well, you can open an issue and so that we can talk about it. Because we're not, I mean, basically the infection core team is not going to try to solve a problem if there is no complaint about it. IO-bound framework. This is more about infection itself, in the sense that in PHP, it's going to mutate a whole new process. I mean, create a new process and change the code in there, run the test, and then kill that process. And it's going to do that for every mutant. So of course, there is a big overhead. We are trying to figure out a way to optimize this, but it's probably always going to be a problem in terms of speed. And you also have the problem of you cannot easily tell if if a given test depends on an external thing like a database or the network. And I mean, as developers, you might already documented and you can know about it, but it's harder for infection to figure it out by itself. So one possible outcome is, for example, that infection applies a mutant that prevents the process to the code to stop early enough, and it's going to run for too long or too fast, and your program is going to run out of memory, and your system may start to kill programs. So, for example, a user was testing things with images, and basically every time he was running infection, Linux was starting to kill PHP Storm and Chrome because it was running out of memory. Infection now limits the memory being used to prevent this sort of problem, but you need to be careful depending on what level of interaction it is, because infection cannot create a database for you, and if you're going to have different connections to a database that might create problems. So, to wrap it up, what I find is really great about infection on personal level is that it gives feedback on your test. Whatever you think your level as a developer is, regardless of how confident you are about your test or not, it's going to give you an objective feedback about it. It allows you to test your test in essence, with very little effort. You just have a little bit of configuration to do, be patient, and that's it. It's quite automatic. It allows you to discover dead code, not as code that's never being run, but more as redundant tests or tests that don't test anything. If you have a given project with mutation score, you remove half the test, and you get the same mutation score, you know that half those tests were completely useless. So that's really beneficial if you want to cut down a bit on the number of tests you have to make sure that you only have the strict necessary. And so it helps you, in essence, to refactor your test. Now, the not so good part is, it is a bit slow. It's still relatively young. The mutants are quite simple, and while we didn't really try yet if there is any way to make them a bit smarter, I try to write more advanced mutants or allow people to write mutants in the application depending on their needs. And you have potential side effects with integration tests. Usually most users just run it on unit tests because they're super fast, there is no side effects, but some are running it on integration tests with DB connections, and you need to be a bit more careful about that. On personal experience, what I really like about that tool, for me, is that it forced me to write tests. I think I'm testing my code a lot, but sometimes I'm also a bit lazy, and I think that, this case cannot happen, it's going to be fine. And I run infection, and turns out that, no, there's a bug there. I always found bugs with it, sometimes really silly bugs that didn't really affect much the users, but quite a few of them were really nasty bugs that were hard to capture and test, but I can imagine much harder to figure out if a user just reported the bug and, well, just to find the bug, be able to produce it, it just can be a nightmare, and this tool helped out a lot for doing that. And also found that it's helpful for non-developer people, like a project manager of some sort, or just the rest of your company or team, to give an objective metric that helps to assess the quality of your code. It's not an absolute metric, but it's a metric like another. It can help out to get a reference rather than just a gut feeling about how good your tests are or not. So in short, use it. And if you have trouble with it, well, feel free to give some feedback. I also created a repository that contains a lot of resources about the mutation testing tools across different languages. So if you're using Go, Haskell, Rust, whatever, you probably can find a mutation testing tool there as well. There's some research papers as well. And you can also give some feedback on LinkedIn, I guess. Thank you.
Yeah, there are lots of questions, but luckily you answered most of them during the talk, so that's cool.
Perfect.
I guess one of the most voted ones is like, okay, you have an application or a set of applications. What sort of like code, in your experience, would be the first ones to like try to introduce these techniques?
It depends how you organize your application, but I guess the first part will be like the core services and aggregates, because they're usually the part that you already tested, and it's the part that's the most important one. Was like a small comment that you don't run often, it's easy to test, well, you care less about it. So yeah, focus more on the important code first.
So then they're asking which team you support, either snake case or camel case for like the functions in tests?
Well, I think it's personal preference. Stick to whatever convention there is. I like the snake case just for the test because I find it more readable. But yeah, it's not necessarily the way you should do it. It's more the way you feel it should be done and how the convention already adopted. It's not worth changing a whole code base just for that.
Yeah. And then a final one. So people are asking like if there is a way to run all these mutations but using separate machines, perhaps like, picking different sets of code or things like that?
It's something I was thinking of. It's requiring some, refactoring within infection, which I'm working on. So it might be possible in the future, but not right now.
Okay. And then a final one, like, is there any flag to limit the maximum number of mutations, trying to reduce the amount of time?
There is not really a flag yet, but you can definitely just limit the number, which mutator to apply. Some mutators do things you're not interested in. You can disable them and reduce the number of files it's applied to.
Okay, cool. Then thank you very much, Théo.
Thank you.